Good afternoon, everyone. We're going to go ahead and get started. So I'll start off by welcoming you all, and thank you for attending the College of Natural Sciences webinar. My name is Allison Sherwood. I'm the Interim Associate Dean for the college. And through our Pilina Ao webinar series, we're aiming to reach the broader community and share the world-class research that happens both within the College of Natural Sciences and with other units here on the UHM campus. Today's presentation features Dr. Michael Liu, who's an astronomy professor at the Institute for Astronomy at the University of Hawaii. He's going to be speaking to us about imaging exoplanets. Michael Liu is an astronomy professor at the Institute for Astronomy. He was born and raised in Washington, D.C. He did his undergraduate degree at Cornell University, and the frigid winters there drove him to sunny UC Berkeley for his doctoral work. He completed his westward migration by moving to the University of Hawaii, first as the Beatrice Watson Parent Fellow and then Hubble Fellow, before joining the faculty there. Mike's research focuses on substellar objects, namely exosolar planets and brown dwarfs. Liu uses the world's best ground-based and space-based telescopes to study their properties, probe their formation, and understand their diversity. His honors include an Alfred P. Sloan Fellowship and the UH Regents Medal for Excellence in Research. When he's not doing astronomy, he enjoys cooking, playing basketball, and spending time with his family. And so please feel free as we proceed with our presentation today. If you have questions, you can enter them in the chat box during Dr. Liu's presentation, and we'll get to those at the end. And at that time, you'll also have the opportunity, if you prefer, just to unmute yourself and ask questions directly. And so at this point, I would like to turn our presentation over to Dr. Liu.
Great. Thanks for the introduction, Allison. Thanks to everyone for taking some time out of your afternoon to come hear about what I think is a very exciting topic. So let me share my screen with you. Here. Okay, I think you all can see my first slide, is that right? Okay, so I'm going to tell you today about imaging exoplanets, what's been happening in this very exciting field recently, and also what we have to look forward to. Let me start way in the past, before there were even telescopes. Planets are special things. They've always been special things. When people first started looking at the night sky, they recognized that there were 7 things in the heavens that didn't move like the stars. There were 5 planets. They could see Mercury, Venus, Mars, Jupiter, and Saturn. They could see the moon, and they could see the sun. So these 7 things were special. They moved in a different way. Planets is the Greek word for wanderer, and the reason for that is that the planets wander in the sky, whereas the stars basically stay fixed relative to one another. And even way back when, people wondered, what was out there in the sky. And so ancient philosophers, for instance, Democritus, the Greek philosopher who actually came up with the idea of the atom, he wrote, "In some worlds, there is no sun and moon. In others, they are larger than in our world, and in others more numerous. In some parts, there are more worlds, in others fewer. In some parts, they are arising, in others failing. There are some worlds devoid of living creatures or plants or any moisture." So he saw the universe as full of different worlds, and those worlds might have different realizations than we see it. Now, of course, the Greeks were philosophers. There wasn't a lot of astronomical data. So with the same observations, opposing views were just as likely. Aristotle's view was there cannot be more worlds than one. So Aristotle was a very bright guy, but in this one he got wrong. Okay, so let me set the stage by just briefly introducing you to our own solar system. Here's a view of the sun on the left, the edge of the sun, and the 8 planets shown to scale in terms of their radius, not of course according to their spacing. So planets in our solar system basically fall into 3 classes. The innermost planets, Mercury, Venus, Earth, and Mars, they're small, they're rocky, they have a solid surface you could stand on, and they're warm because they're close to the sun. They get a lot of light. Uranus and Neptune, the so-called ice giants, mostly made out of gas, farther out and significantly larger than the rocky planets on the inside. And then finally, Jupiter and Saturn, the really big, most massive, largest planets in our solar system. They're mostly made out of hydrogen and helium gas. And so 26 years ago, this was all we knew about planets, were the 8 planets in our solar system in these three different types. But even then, we had an idea that our picture was incomplete. To be a scientist, one of the tricks of being a scientist, it's not that difficult, is you plot down everything you know, and you ask, is something missing? So 26 years ago, if you had made a plot of all the things floating out there, some representation might have looked like this. There were stars, like the sun. Of course, stars come in many different masses. But the smallest stars we knew about were these so-called M dwarfs, or red dwarf stars, very faint stars, about 10% of the mass of the sun. And then there's this huge gap in mass. And so you went all the way down to Jupiter, which is 0.1% of the mass of the sun. So you might just ask, given that I know that there are all these things more massive than the sun and more massive than M dwarfs, and there's Jupiter and a whole bunch of smaller planets, is there anything in between? And people theorized at the time that there was a class of objects they called failed stars or brown dwarfs. And the reason why is that, as you probably know, the sun generates energy because it's so massive. The interior gets so hot that hydrogen fuses into helium. But there's a minimum mass for that, and that minimum mass is about 8% the mass of the sun. So any body less than 8% of the mass of the sun could still be this big floating gas cloud, but it would not generate energy. So we suspected something like that might exist. But there was a big gap. Now, one of the fun things about astronomy as a science is that in astronomy, about every 5 or 10 years, something will be found or something that will be realized that just completely changes the field. Like it's almost like the snap of your fingers. And I've been around this business long enough to have seen this happen about 2 or 3 times. And one of those times was 1995. Okay, so 1995 was Annus Mirabilis, so-called miracle year for astronomy. Because in that year, and actually at the very same conference, 2 objects were announced that people had wondered had existed, if they'd even existed for thousands of years. On the right is this object GL229b. It's a brown dwarf. It's one of these failed stars. In this case, it's about 7% the mass of the sun. It's a companion around another star, one of these red dwarfs. And here's a picture taken of it. So we see it in light. And then on the right is this is a planet 51 Peg B. It's the first exoplanet discovered around a sun-like star. And we didn't take a picture of it. The way that worked was that by precisely monitoring the velocity of this star, 51 Peg, which is a star like the sun, over time, very precise velocity measurements could determine that the star was going back and forth and back and forth and back and forth in a repeated periodic fashion, indicating the gravitational tugging of something very, very small and something very, very close to the central star. And that's the planet 51 Peg B. Okay, so in a fell swoop at one conference, these 2 mystery objects, which people had wondered if they'd ever existed at all, we now knew they existed. Okay, so this picture where we have this gap between the lowest mass stars and the highest mass planet that we know about, Jupiter, was closed in the 1990s. In fact, in the 90s, we found 2 classes of these brown dwarfs, one the so-called L dwarf, a lot of dust in their atmosphere, another a T dwarf, a lot of methane in its atmosphere, and we found that there were other planets like our Jupiter or more massive than our Jupiter, so we found there were many, many Jupiters. So in a fell swoop, we found these things. Even better, 13 years later, there was another miracle year, and that brings us to the topic of today's discussion, and that is imaging planets. So in that year, 4 planets were announced that people took pictures of. They imaged them directly. They weren't studying the tug of the star to determine the presence of an unseen companion. They were actually able to image the light coming from a planetary companion. And these are the 4 shown here: HR 8799, Beta Pictoris, Fomalhaut B, and RxJ 1609. So this truly was a miraculous year, a second miraculous year for those of us interested in this topic. Let me just show you perhaps the highlight of this is the so-called HR 8799 system. It's a star about 100 light years away. It's spectacular because it has 4 planets orbiting around it. Each planet has a mass of about 5 to 7 Jupiter masses, and they actually go in mostly circular orbits around the central star. In this image, you see the 4 planets here, labeled B, C, D, and E. The central star has been blotted out. It is much, much, much brighter, as I'll explain. and it's been removed through a combination of our instruments and also our software. Okay, and this discovery was made using the telescopes on Mauna Kea, both the Gemini telescope and the Keck telescope. Before I tell you about what we've learned from these images, let me spend some time telling you about how exactly we found these things, the technologies behind them. There are basically two ways to find planets around other stars. The first way is a general class, so-called indirect detection, and this by far has produced the most planet discoveries, thousands of them. In these, you study the star in order to figure out that there's a planet around the star. You figure it out indirectly. You don't directly detect the planet. So for instance, if the star moves back and forth in velocity in a repeated periodic fashion, the star wobbles, so to speak, you measure its velocity, that's a sign that something is tugging on it. And depending on how strong that tug is, how strong the velocity changes, you can determine if it's a brown dwarf or a planet. You can also monitor the brightness of a star. And if something passes in front of the star, if there's a planet orbiting that star, it'll blot out part of the light. And you can, by measuring the total brightness of the star, you see it goes down a little bit and then comes back up and does so periodically, so-called transit. The planet crosses the face of the star. That's another way you can detect it indirectly. And there's another phenomenon where, in fact, the star can get brighter due to a phenomenon known as microlensing, which I'm not going to get into. But these are all indirect. You study the star very, very closely and infer a planet is there. The other class is so-called direct detection. You actually take a picture of a planet. There's a relatively small number of discoveries, only a few dozen now, but it's very, very precious. Now, you might wonder, why is it so hard to take a picture of a planet around another star? There are two basic reasons.
They're a long ways away.
That's the second reason. I'll get to that. The first reason is that they're very faint. Okay, if you look at what the brightness of the Earth is relative to the sun, it's a factor of 1 billion. Okay, so the light reflected off the Earth, which is just reflected starlight, is 1 billion times fainter than the sun. So imagine seeing something, trying to see something 1 billion times fainter than something else. It's really hard. The second reason relates to the fact that stars are very far away, and that is that the separation is very small. Projected on the sky, the planet is very, very close to the star. So you have to look at something that's 1 billion times fainter, and it's right next to the thing. People talk about trying to see a firefly in front of a car headlight. It's even worse than that. Okay. One analogy I like to use is if you scale down the universe by a factor of 1 billion to 1, if you can imagine the separation between the Earth and the sun, that's 93 million miles. The Earth would be the tip of a ballpoint pen. The sun would be a grapefruit or a pomelo. You separate them by 50 feet. Okay, so you've got a pomelo in Hawaii. 50 feet away, you've got a tip of a ballpoint pen. And you're standing in California trying to image the space between those two objects. Okay, it's really, really, really hard. Distinguishing something 50 feet apart from the 2,500 miles it is to California. Okay, so it's a doubly challenging problem. They're very close together, and also the planet is very faint relative to the star. How do we solve this problem? Okay, one of the key technologies in doing this is so-called adaptive optics. The Earth's atmosphere is great. It keeps us alive, it keeps us warm, it's a nice comfortable blanket for us. But astronomers, or at least astronomy, hates it. And that's because the light from stars that passes through the atmosphere is corrupted. The atmosphere is turbulent, it's swirling around, it bends all the light. On the right here, if you look at an image of a star and you take many, many exposures, hundreds to thousands of exposures per second, you see that a single star, which looks like a dot of light, if you were to zoom in, breaks up into this huge clouds of dancing dots. We call them speckles. And the reason why they're dancing around is because the atmosphere is always changing. The atmosphere acts like a lens, bends the light, and so the position changes. In the same way that if you look at a really hot road on a really hot day, you look at it horizontally, you can see that the image of the road seems to shimmer, and that's because the light is passing through the atmosphere and its path is being bent. The same thing happens for light, astronomical light passing through the turbulent Earth's atmosphere. Adaptive optics is a technology that will fix this. And so you see on the right, and I'll explain how that works, but basically it concentrates the light, it senses the behavior of the atmosphere and fixes, rebends all the light back in the same place. Now it doesn't work perfectly. As you can see, the star still flickers and it drifts a little bit, but it's a whole lot better. If you were to take a long exposure picture of the thing on the left, you get a big, giant, fuzzy blob, but here you get a sharp dot of light. Now, how does this all work? Okay, so this movie is an illustration of how this whole adaptive optics system works. Okay, so here's an illustration of a telescope, modern telescope, and the stuff moving around is a representation of the starlight. Okay, so it bounces off the big mirror of the telescope, the primary mirror, bounces off a smaller mirror called the secondary, and then goes down through a hole in the primary mirror where the astronomical instruments are stored. And so if we zoom in on these instruments, this is a representation of the adaptive optics system on the Gemini telescope on Mauna Kea. Here's a computer. Computer represents the astronomer. And the light comes in, and ordinarily, okay, so the light goes through some optical system. It goes off some mirrors and lenses. And the light is collected by a detector, much like the detector in your cell phone that you use to make movies. And so you can see the atmosphere bends the light. And so the image of the star dances around. Now, if you zoom in, one way to think about light is that light is a wave. A light is a perfect sheet, and that sheet gets distorted by the atmosphere. It gets bent into a potato chip. So what adaptive optics does is it takes part of that light, measures the shape of those potato chips, sends signals to a deformable mirror, a mirror that changes shape tens to hundreds of times per second to form an anti-potato chip. So when these crinkled wavefronts of light bounce off it, they're straightened out, they're fixed, they're flattened. And so instead of getting dancey, fuzzing images, you get, in the end, nice sharp images. Okay, so this is how adaptive optics works. Hundreds to thousands of times per second, it's measuring the shape of the light that's coming into the telescope. A deformable mirror is continually changing shape, a little piece of glass that bends the shape of its surface to counteract this distortion. And so, for instance, here's an image of Neptune. And if you took it with ordinary images, even from a very good, clear site like Mauna Kea, it'd be mostly a fuzzy blob, and adaptive optics sharpens things right up. So in this case, you can see weather and clouds on the surface, in the atmosphere of Neptune. All right, so closer to the things we care about, here's an image of a very bright star. This is a sun-like star. It's known as HR 7672. This huge blob is after you've fixed it with adaptive optics. Okay, so it's really zoomed in. It's not a perfect image, but without adaptive optics, this whole slide would be filled with nothing but white. And this little dot here is a 60 Jupiter mass brown dwarf next to this sun-like star that we imaged with adaptive optics many years ago. This dot is 2,000 times fainter than the primary star. Okay, so adaptive optics is a key technology. I should mention that, like all technologies, we're always looking to improve things. One way in which things are being improved, I want to highlight a little bit of work by my faculty colleague, Michael Bottom, who's located at our facility in Hilo. He's been looking at ways. I showed you a picture of adaptive optics, which fixes the whole image of the star. And he's been looking at advanced ways to fix things even better, to remove the leftover lumps and bumps. We call them speckles. And here's an illustration of some work in the laboratory with some new algorithms, basically to do more sophisticated sensing of the star, called speckle suppression. So you can focus on a zone, and in that zone, you can do even better at removing the starlight from the primary star. You can do this in a number of different ways. This is a different technique called speckle nulling, but the idea behind speckle nulling is that instead of trying to fix the whole of the area around the star, removing all its light, you just fix half the image, and by fixing that half, you can do an even better job. So here's an example. This is the before image. Here's the star with all the stuff that's uncorrected by the adaptive optics system, so the leftover stuff. And with speckle nulling, the sort of iterative process, you can carve out a very, very dark region. Very good for finding faint things around stars. Okay, so technology is very, very important. This adaptive optics technology. The other thing which is important that allows you to take pictures is you have to look at the right kinds of stars. If you look at how things cool over time, okay, so this is a representation of the luminosity, that is just the brightness or the energy coming out of an object as they age over time. Stars like the sun or stars like red dwarfs, they start off a little bit brighter and then they flatten out. And they flatten out, which is good for us because the sun is always basically producing the same amount of energy. So for 10 billion years, it's going to produce 5 billion that had preceded it. Another 5 billion more produces the same amount of energy because it has this stable engine to fuse hydrogen into helium. Brown dwarfs can't do that. They're failed stars, so they're bright at some point, but then they cool off over time. In the same way, if you take a piece of charcoal out of the grill, it starts off hot and it cools off. That's what brown dwarfs do. They have residual heat trapped in them, so they cool off over time. And planets do a very similar thing. Now, most stars that you look at in the sky, or most stars that are close to us, are very old. They're billions of years old. And so that means the brightness difference between the central star and the planets is very, very large, million or billion to one. So it's very hard to see the planets around these very old stars because these planets have faded. They've spent billions of years cooling off, and so they're difficult to see. So you need to look at the right kinds of stars. You need to find stars that are not billions of years old, but rather millions of years old. So in this case, the contrast, the difference in brightness between the planet and the star is much smaller. Instead of a billion or a million to one, maybe it's only a million to one or 100,000 or even 10,000 to one. So that's been another part of the big story as well, is finding the right kinds of stars. This is a map. It's a map of the sky. So it's like a globe like the Earth, but it's the celestial sphere. And each of these dots here are basically young stars that through a variety of different techniques, we have identified, there are hundreds of thousands of stars in the immediate solar neighborhood close to us, but only about 1% of them are young enough to do this experiment, to image planets around other stars. So this was work that I've done over a number of years, first with Caitlin Allers, who was a postdoc at the University of Hawaii, and then Kimberly Aller, no relation to Caitlin Allers, who was a PhD student of mine as well. And they were very good at finding these young stars, figuring out which stars in the sky were the right ones to look at. Okay, so you have the right technology and you have the right stars. One point, okay, so now I'm going to talk about what we found, but one point I want to make clear, just so we're all on the same wavelength, is that there are two kinds of light we're going to talk about. When we see things with our eyes, we're looking at so-called visible radiation or visible light. We see things by reflection mostly. So light from the sun comes in, bounces off something and comes into our eye, in this case, a pig. Okay. Other kinds of radiation is emitted radiation, like infrared radiation, like heat. If you were to have an infrared camera to look at the same pig, it would be glowing. When you take a piece of coal out of the charcoal, out of the barbecue, it's still glowing. That's emitted radiation. Okay. So when we see things in the night sky, when we see the moon with our eyes, or we see, in this case, Jupiter, I think it is in this picture, the moon and Jupiter, we see reflected light, we see starlight, we see sunlight that bounces off the moon and comes into our eye. The astronomical images I'm going to show you when we take pictures of planets, we see emitted radiation. We see the heat left over from the planets that's being directly radiated by the planet itself. Okay. So let me tell you a few things that we found. Okay, so let's come back to our friend HR 8799. This is a great sort of case study to illustrate what we can learn. So one of the first things we discovered about this planetary system is if we just compare the scale, the physical size of the 8799 solar system to that of our own solar system. So these are two things at the same scale. So the 8799 planets, these are 5 to 7 Jupiter masses. They're really massive. This red dot here on the right represents Jupiter, 1 Jupiter mass, okay? And you can see Jupiter and even Saturn, Uranus, and Neptune are all closer in. The Earth and the Mars are all mushed in here very closely. So the planets that we found imaged so far, they're much further out. Jupiter's at 5 astronomical units, 5 times the distance from the Earth to the sun. The 8799 planets are out to 60 astronomical units. So the whole solar system around this star is just a whole lot bigger. Now, we just don't only take pictures, we can also take movies. So you come back and you re-image these things over many, many years. And here's a movie which illustrates the orbits of the 8799 planets. So this is 7 years worth of data. The 4 planets you can see, they actually orbit the star in the same way that the planets in our own solar system orbit the sun. And from these sorts of measurements, from these partial orbital arcs, you can learn things, for instance, about what the shape of the orbits are, and that tells you something about how the planets formed, and also the gravitational interaction of these 4 planets. They jostle each other around. We can study those also by looking at their motions. So we've acquired, like I said, there's a couple dozen of these things that have been imaged to date. Here's a picture album which shows some of them. So here's the 4 planetary system, 8799, and each of these has their own phone number and so forth. But there's there's a mix of them. They're typically many Jupiter masses and typically tens to even hundreds of times farther from their star than the Earth is from the sun. So much, much further out than Jupiter, and typically much more massive. I should highlight the latest discovery. One of my favorites is this system known as Coconuts 2. Coconuts 2 is the nearest directly imaged exoplanet to Earth. This is an image of the sky. It's a very crowded field of the sky. And this star right here is Coconuts 2a, the host star. It's a star about a third of the mass of the sun. And this little red dot here is Coconuts 2b, the planet. It's about 6 Jupiter masses. It has a projected separation of 6,000 astronomical units. So 6,000 times farther than the Earth is from the sun. This is a hugely, hugely separated planet, discovered as part of the PhD thesis work of Zijie Zhang, one of my recent PhD students. The Coconut system is a crazy system. And one of the things is because the planet is so very, very far from the star. Okay, so here's an artist's illustration. It's a 6 Jupiter mass, gas giant planet here. It's so far away that the host star that it orbits looks just like a regular star in the sky. So the daytime, there's no solid surface on Coconuts 2b, but if you were floating in the atmosphere of Coconuts 2b, when it's quote unquote daytime, it's just as dark as it is at night. And this artist's illustration tries to convey that. The host star would look like a bright red star. It would probably be the brightest or second brightest star in the sky. But there might be Canopus, which is a southern star, is probably equally bright if you were at Coconuts 2. So in fact, at night, there would be these 2 bright stars in the sky, but basically it would always be nighttime on this planet. So it's a very, very cold, very distant world. Now, one of our goals is to compile a so-called census of extrasolar planets in the same way that the government every 10 years takes a census and asks a question of, who's living in the US. We want to know all the different properties of exoplanets that are out there. And this census, has a number of natural questions. How many extrasolar planets are there? How many planets are there around other stars? How common are they? How frequently do they occur? What is their masses? Are they big planets? Are they small planets? Are they somewhere in between? What are their shapes of their orbits? Are they mostly circular, like in our own solar system, or might they be elliptical? And that tells us something about how they formed and interacted with each other. What kinds of stars are they around? Are planets more common around stars like the sun? Are they more common around planets like, around stars that are like these low mass red dwarf stars? What are they made out of? We know they're mostly gas, but what is the mix of those gases? And then of course, probably the single most compelling question of all, who might be living on these planets? Okay, so let me show you one way in which we can get at just one of these questions. Okay, so this is an illustration which shows a few of the imaged planets to date. I've shown Jupiter here at 5 astronomical units, and this is the host star, and this is the projected separation from the host star. Here's 8799, this 4-planet system I talked about, and here are a few others. Coconuts 2b would be out here. We know that planets were born when the stars were young, only a few million years old, in a disk of material, gas and dust and little rocks. And this gray area is a representation of that disk. So one thing you'll learn is that because there are planets farther out than the sizes of these disks that we know about, is they probably moved, right? These planets didn't form out here. They probably formed in here and somehow got kicked out due to interactions with younger planets. Another thing we know is that these disks, the material in the disks changes as you move farther and farther away from the star. And let me show you an example. So the star is very bright when it's young, and that means it's hotter when it's close to the star and colder farther out. So if you imagine water, just water floating around in these in these disks, close to the star, it'll be in vapor form, it'll be gaseous. But farther out where it's very cold, the water turns to ice. So you have little bits of rocks and bits of ice that help put together the planets. And if you consider the different molecules that might be abundant in these disks, they also might be gaseous or they might be icy at different distances from the distance of the star. So for instance, CO2 is condenses at even colder temperatures. So the region in which CO2 was gaseous in these primordial disks was larger and icy out there. And then also perhaps CO as well. So although these planets moved around to where these very large separations where we see them now, if we could figure out the compositions of these planets, by measuring the abundances of these trace gases, we might figure out where they formed originally, because where they formed originally, the material they formed out of, the rocks and the ices they formed out of changes as a function of distance from the star. Okay, so this is a very important question. Where did they form? How did they form? And so from a practical standpoint, how would you ever figure out what the composition of a planet is that you took a picture of? The way we do this is a technique known as spectroscopy. You may know that light, when you look at sunlight, it's actually made up of many, many colors. So if you pass the light of the sun through a prism, it spreads out into a rainbow. And the reason why is the material in the prism, the material it's made out of, bends the light, but that bending, the amount of bending depends on the color. And so blue light is bent more, red light is bent less, and so it's spread out into this rainbow of colors that we call spectrum. Okay, so this is for starlight. You're all very familiar with this. Of course, we all live in Hawaii. Every time you look at a rainbow, right, that's a spectrum as well. In the case of the rainbow, the prism are little water droplets in clouds that are spreading out the light. So we use spectrographs, which have prisms or have other optical elements to spread out the light. Now, if you spread out the light a little bit, you might get, the colors are close together, but if you spread it out really, really broad, you can see incredibly detailed information. Here's a spectrum of the sun. Okay, so we've passed the light of the sun through a dispersing element and spread it out, and then we've actually cut it into bits and stacked it on top of each other. Okay, this is a spectrum of the sun. Sunlight is mostly continuous in color, but if you spread out the light far enough, you can see little wavelengths are missing. There's less light at these points. And these are the chemical fingerprints of trace atoms present in the atmosphere of the sun. The sun is mostly hydrogen, but there are little bits of things like sodium and magnesium, calcium that are present in the atmosphere of the sun. And they absorb the light on the way out as the sunlight is leaving. And so they leave little fingerprints through the absence of sunlight. If you were to make a plot of this, if you were to run a line along this spectrum and make a plot of how bright it is, it would look something like this. So on the x-axis is color or wavelength, and the y-axis is just how much the intensity, how bright it is. Okay, so here's the spectrum of the sun. To the left is bluer light, to the right is redder light. And it mostly is bright, but it has these little notches, okay? And each of these notches is the chemical fingerprint of something that has absorbed the sunlight on the way to us. The D lines are sodium, the B lines are magnesium, H and K is calcium, so forth and so on, okay? So we take spectra of things. We take spectra of stars, we take spectra of brown dwarfs, we take spectra of planets to look for these trace elements to figure out what they're composed of. All right, so let's come back to our friend 8799. Shortly after the discovery of 8799, one of my graduate students at the time, Brendan Bowler, and I set out to take a spectrum of the planets. We wanted to figure out what's going on in them. Taking the picture is nice, the picture is good, you figure out how bright the planet is, how hot it is, but you want to figure out more about it, you have to get a spectrum. Okay, so we use the instrument known as OSIRIS, which I won't go into, but OSIRIS is very good at taking spectra of exoplanets. And so here's the spectrum. It doesn't look like the spectrum of the sun. We had many fewer data points, just a dozen data points basically, but this is similar to the plot I just showed you. This is the wavelength or the color of the light, and this is the brightness of the planet. And it has an overall dip in it. And that dip is potentially the signature of methane in the atmosphere of the planet. The spectra tells us about the gas, the gaseous atmosphere of the planet. If you were to imagine as a cartoon, you could take a core sample, like, a slice of the atmosphere of these planets, what might they look like? Here's an illustration. So this is the top of the planet, and this is you go into the inside. We know that these planets probably have clouds in the same way that Jupiter has clouds, Neptune has clouds, the Earth has clouds. The clouds are a different composition. We think they're probably made of small little bits of basically metal, condensed metal, condensed iron or magnesiums or silicates. And then potentially CO, carbon monoxide, and methane. Okay, so through this spectroscopy is how we figure out the presence of trace gases like methane, and also the overall shape of the spectrum tells us something about the clouds. So this spectrum was pretty simple. We only had a dozen data points. Follow-up work by another group with the same instrument spread out the light even farther, got hundreds of data points now, and here's their spectrum. So this little comb of lines, these are the molecular fingerprints now of molecules like water, methane, and CO. They actually had many, many, many lines, not just a small number of lines. And so from this higher resolution spectra, we can try to figure out what is the abundance of these atoms like carbon and oxygen, and thereby trace how did these planets form. Okay, so that's a look at sort of what we've found to date, and also some of the things that we can learn by monitoring, say, the orbits of these planets and also getting spectra. What's next? The amount that we know from imaging about planets around other stars is a tiny, tiny fraction of what we would like to know. This is a picture of Saturn taken by spacecraft. And if you think about all the things that could be going on in Saturn, there's an incredible number of things that the planet is going on. The planet is rotating. It has clouds on its surface. Those clouds change. There's weather. There's photochemistry, and that is that the light from the sun, when the light from the sun strikes the surface of Saturn, it induces chemical reactions in its atmosphere. Saturn itself is emitting heat. And then we'd like to know things about how massive the planets are, what they're made out of. In this case, Saturn has rings. Maybe some extrasolar planets also have rings. Okay, so there's a lot of stuff we'd like that we still can't know. We're just at the tip of the iceberg with these things. In the same way, if you look at the census, the current census of planets that exist, we're only taking pictures. We're only imaging a tiny fraction of the number of known planets. Okay, so here's a plot which illustrates the separation. This is now in physical units, it's astronomical units, distance of the planet from the host star, as a function of mass in Earth masses. So these little dots here, V and E, are Venus and Earth. And here's Uranus and Neptune and Jupiter and Saturn. This sea of points are the planets detected by the indirect methods, the transit method and the radial velocity method. And here's the imaging method. Most of these are brown dwarfs and some of them are planets. Okay, the image planets are further out, as you can see, and they're also higher up on the plot. So they're much larger in mass. There are many Jupiter masses. Earth is all the way down here. It's very close in and very, very small. You know, it's thousands of times less massive and hundreds of times closer than the planets we've imaged today. If you look at the abundances of planets, simply how many planets there are, what is the distribution of planets? This is another representation. This just shows now the radius of the planet. And this is just a histogram which shows the frequency. This is actually work done by B.J. Fulton, who is a PhD student. Forgot to include BJ's picture. But in fact, you know, the Jupiter planets are all the way out here. They are relatively rare. The planets we're seeing are very rare. Most planets are so-called sub-Neptune planets. That is, they have a size about, radius about 3 times that of the Earth, and so-called super-Earth planets, 1 to 2 times the size of the Earth. So we have not taken pictures yet of the most common types of planets. Or put another way, nothing we have imaged to date looks like any of the planets in our own solar system. Okay, so this is a very famous picture. This is a picture that the Voyager spacecraft took when it was leaving the solar system, looking back at the planets. Okay, so here's Jupiter, and here's Earth, this tiny little dot. We can't make these images yet of other planets around other stars, but we want to. Let me show an illustration of how far, you know, what we've accomplished to date and where we want to go. This now shows the separation. In this case, it's angular separation, just projected separation on the sky. And this is the contrast. This is how bright the planet is relative to the host star. These are some of the planets we've imaged to date. So they are about 10,000, 100,000 to 1 million times fainter than their host star, made possible with this great technology, adaptive optics, and choosing the right stars. If you go down by another factor of 1,000, down to 1 billion to 1, then you can start imaging some of these closer in planets, these rocky planets that have been discovered by indirect methods. So you can turn indirect planets into direct planets if you could get 1,000 times, find things 1,000 times fainter and a factor of a few closer in. And then if you want to get to our own solar system, it gets even harder. Okay, so you got to get to 1 billion or 10 billion to 1 for our own solar system. What do we need to do this? Well, astronomy is one of those fields of science that is driven very much, big changes in astronomy are driven by big new facilities. And so what we need to really push into this new domain are next generation telescopes. One of the most exciting projects out there is the 30-meter telescope. It's called 30-meter telescope because the primary mirror, this big piece of glass, in this case, it's about 500 segmented hexagons, fit together like a jigsaw puzzle, is 30 meters across, okay, 100 feet. In comparison, the largest telescopes we have now are about 10 meters across. So this is 3 times bigger across. And the aspiration is in the next decade to build this on Mauna. It's big, okay, it's 30 meters across here. Here's a car for scale, and it's very, very powerful. Now, a huge international team is working on the 30-meter telescope. And I just thought I'd highlight Mark Chun, my colleague in Hilo, who's been thinking about how to implement better adaptive optics systems for this telescope. And also Doug Simons, who just today started as director of the IFA, my new boss. Doug has been deeply invested in understanding how to have both science and culture coexist on the summit of Mauna Kea. Okay, so why do we need bigger telescopes? There are a number of reasons, but let me just point to a number of, basically a few simple things. It turns out that because of the properties of light, that the sharpness, the very sharpest image you can possibly make depends on how large an aperture that light goes through, or how large a mirror that goes through. The bigger the mirror the light goes through, the sharper the image you can make. And so the sharpness of an image is linearly proportional to the diameter of the telescope. If you go from the Keck telescope to the 30-meter telescope, from a 10-meter mirror to a 30-meter mirror, you can make a 3 times sharper image with that larger telescope. In the same way, if you look at the amount of light that a telescope collects, the light bucket, that depends on the square of the diameter of the telescope. So the 30-meter telescope will collect 9 times as much light as our largest existing telescopes. And then actually to identify a point source, that is a dot, like a faint planet, detection of point sources actually scales as the diameter to the 4th power. So TMT will actually be 81 times more powerful than our largest telescopes for finding faint dots around bright stars. Now, you can do lots of great science in all pieces of the universe with the 30-meter telescope. Specifically for imaging exoplanets, TMT is going to open 2 arenas that we're just, we can't get to quite yet. The first arena is the time arena. I told you that planets form at ages of a few million years. Okay, they're basically being assembled in these disks around young stars. And here's an artist's illustration. This shows a disk of gas and dust around a young star. And here you see a planet like Jupiter in the process of coming together. We have theories as to how this happened. We have images from radio telescopes which actually show these disks of gas and dust. And here's one such image which have these regions of less material. And we suspect that part of the reason for this is that planets could be forming, taking that material in that ring and coming together. And we want to image those planets. And that's why you need a telescope which can make sharper images and find things that are even fainter, opening the time window to see planets as they're coming together. So that's one avenue. The second thing that TMT opens up for you is the ability to get to much smaller planets. Like I said, the planets we're imaging now are gaseous planets. They're Jupiter mass or many times the mass of Jupiter, but we want to study rocky planets like the Earth, okay? TMT, it will be possible with TMT and an advanced suite of instruments to actually take pictures of rocky planets. So here we won't be seeing the emitted light, we won't be seeing the heat, we'll actually be seeing the reflected light in the same way that when we look at planets in the night sky, we see our sunlight bouncing off that planet, going into our eye. We may be able to see habitable planets around nearby, very close, low mass stars, but the light from the low mass star bounces off that rocky planet and comes to our telescope. The stars have to be very close by, so the planet separation from the star is large on the sky. Low mass stars are light because they're not very bright, okay, so that makes it easier to see the planet. And it's an extra bonus if the planet is in just the right place, the so-called habitable zone. Those planets might actually be habitable. If a planet is too close to its central star, the planet's too hot, atmosphere bakes off, the surface is molten lava, nothing can live there. If the planet is too far away, it's frozen over, the whole surface is covered in ice, nothing can live there. But if it's just the right place, where the planet is just warm enough, it can have liquid water, it can have an atmosphere, it could be habitable. So we want to image rocky planets, we want to image them around nearby low mass stars, and we want to image them at just the right distance from their star so that they might be life-sustaining. Okay, so TMT opens the possibility of that. You can do all kinds of fun things. I told you about spectroscopy. Well, spectroscopy, if you take many, many epochs in spectroscopy, take spectra of the same planet over and over again, as that planet rotates, if it has spots, if it has clouds, those come in and out of view. So the spectrum changes over time. And using some sophisticated algorithms, if you take this whole sequence of spectra over many, many hours, you can figure out what the surface of the planet, what the brightness of the planet looks like from this long time series of spectra. So here's an illustration of this. This has been done. This is for a nearby brown dwarf, where many, many spectra were taken, and then it was inferred, reconstructed through some algorithms as to what the brightness of this, PowerPoint didn't like that. Okay, let me relaunch my PowerPoint. All right. Let's see here. Here we go. 1 second. Okay. Slowly, here we go, coming back. Okay. Okay, I won't put that movie again in case it's jinxed. But the idea is, you can see, you can map the surface of the planet. The second thing you can do with spectroscopy, oh, hold on, I'll share my screen. Here we go. Okay, another spectacular thing you can do with these very large telescopes is you can get very high precision spectra. You can spread the light out really, really far. The planets are faint, you need to collect a lot of light. You can look for so-called biomarkers. Certain gases, or the abundances of certain gases, can only be explained if there's life on a planet. Can't be explained by geology, okay? You need life to generate certain gases in certain abundances. So with a large enough telescope and an advanced enough spectrograph, you could take spectra, and here's an illustration of these different spectra. So again, the x-axis is the wavelength or the color of the light, the y-axis is the brightness. And these little lumps and bumps are the signatures of different gases. Gases like molecular oxygen, like water, like methane. Okay, so this is one of the holy grails, I think, of doing science with next generation telescopes. We can never, not in our lifetimes at least, go to those planets, but we can remotely sense their atmospheres, figure out the composition of their atmospheres, and look for very, very subtle signatures in their spectra that indicate biological life. And this is a simulation of what, if one of these systems were very close to us, very, very long exposure with some of the large, one of these, a telescope like the TMT, what this might actually look like. In this case, the central star has been processed. It's this funny swirly pattern, but in principle, you might be able to image in reflected light now, something like the Earth. And this would be, truly, truly amazing. Looking beyond that, okay, so that's perhaps, the 2030s, in the decades beyond that, I'll just mention briefly, the ultimate thing to do is, of course, to go beyond the atmosphere and go into space. So NASA has very ambitious plans for, two possible concepts, say 20 or 30 years away, of telescopes which could image rocky planets not around simply low mass stars, but actually stars like the sun, and image many, many more planets. One is called HabEx. It's a 4-meter telescope in space. It's actually 2 pieces. It has this giant floating thing called a star shade, which basically it repositions in front of the star to blot out the star and make it easier to see planets next to it. And even more ambitious, this telescope called LUVOIR, it'd be 15 meters in space. Here's the primary mirror. This is a thing which shields it from the sun. And these would also, this would be incredibly powerful for taking spectra of Earth-like planets around sun-like stars and looking for signs of life. Now, a few years ago, there was a study conducted by the National Academy of Sciences about exoplanets, trying to figure out a global strategy for exoplanets. And one of the findings I wanted to highlight is that they said that the GMT, the Giant Magellan Telescope, another large telescope, and the TMT, the 30-meter telescope, will enable profound advances in imaging and spectroscopy of entire planetary systems over a wide range of masses, semi-major axes, that is how the range of separations from the star, and wavelengths, potentially including temperate, Earth-sized planets orbiting red dwarf stars. So they advise that the National Science Foundation should invest in both these large telescopes and their instrumentation to provide access to the US astronomical community. And so studies are underway now to see if it is possible that the National Science Foundation will actually do this and help make these telescopes possible in the next decade. Okay, so let me just wrap it up. I started by telling you that in the beginning, that planets are special. We've known planets are special. Planets have always been special. They've been special for a long time, and they're special now. We are in an age where we can directly detect and characterize planets around other stars. And so some people have referred to this as the second Copernican revolution. The first Copernican revolution was the realization that the Earth goes around the sun. And now we're in this revolution now where we can actually answer, some of, I think, humanity's very oldest questions. Questions like, how did our planet form? How did the solar system form? Are there planets around other stars? How often do they occur? And is there life out there and elsewhere in the universe? So these are questions that people have been asking for thousands upon thousands of years. And now astronomy, using the world's largest telescopes, we're in this special era that we're beginning to answer these questions directly through science, through astronomy. Great. Thank you for your time, and I welcome your questions.
Wonderful. Thanks so much, Mike. That was a really fantastic talk. I think what we'd like to do is just open up the conversation. So if anyone would like to ask their questions directly, please just unmute yourself. There's also a couple coming in through the chat we can start with.
Sure, there's one question that looked like it was in the middle of the talk. I'm not quite sure of the context. So if you'd like to ask that again, you could. But I'll answer the second question as what is the naming convention for stars? Well, it's kind of this giant hodgepodge. There are some stars that get names, Canopus, Arcturus, and that's because historically somebody wrote down, ancient civilizations wrote down names for those stars and those are attached. Then people started making catalogs of stars. So like HR, blah, 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 blah. That's a catalog. HR is the name of the person, or the people who put together that catalog. And then finally, in the last, many decades, we found so many stars, we can't even catalog them or give them names. We just give them numbers, 12, 17 plus 34. And those names are related to the coordinates of the star, the positions of the stars on the sky. So some stars get names, some get these funny, acronyms, and others just get numbers in the end.
Question.
Yeah.
This is Danny Quintana in Salt Lake. Using Drake's equation, what is the probability of life in just our galaxy, not in all of the galaxies, because there's just so many?
Right. So what Danny's referring to is this thing called the Drake equation, and that's a way to estimate how many intelligent civilizations there are in the universe. So you can do an estimate on a piece of paper if you know how many stars there are, and you know what fraction of stars have planets, and you know what fraction of planets form life, and what fraction of life becomes intelligent, and what fraction of life doesn't destroy itself because it uses up all its resources or blow itself up. You can actually calculate that. Now, the difficulty with Drake's equation is that all those things, most of those things are very hard to know. We know how many stars there are in the sky. We're working hard at the second term, how many planets there are around other stars, that we have down pretty good. But like how often life occurs, how often life becomes intelligent, how often life doesn't blow itself up, those are the things you really don't know, and those are guesses. I think, most astronomers, if you ask them, do you believe there is intelligent life out there in the galaxy? They would say yes, because we know planets are super common. We know there are billions of stars in our galaxy. And so, we anticipate that, we are not a unique miracle in the galaxy, but we don't know, right? We'd like to know. And that's sort of what the goal is to actually be able to directly measure, maybe in my lifetime, how often planets around other stars have signs of life. That's the thing that we're all aiming for. Let's see, another question in the chat. Did you just say that discoveries in the astronomy now are as meaningful as the Copernican revolution? I don't know if I meant to say that. Certainly the Copernican revolution, we realized the planets go around the sun, and the sun wasn't Earth wasn't the center of the universe, was a big deal. But I think we are, I don't want to compare one scientific transformative worldview to another, but we are in a special time where we can count the number of planets around other stars, and we can measure their properties We can figure out how common our Earths around other stars, how common our Jupiters around other stars. So it's a really special epoch in figuring out, where our place is in relative to everything else in the universe. Okay, I can just go through the questions in the chat. When you point the Space Telescope back to Earth, is it possible to detect the biomarkers you're talking about? I think you're asking, if we had a satellite and we pointed that satellite to Earth and we took a spectrum of the Earth, what would we see? Yeah, you can see the signatures of gases in the Earth's atmosphere that are signs of biological life. So that's an easy measurement, of course, because we can get, it's easy to get, put a satellite into orbit, point back at the Earth. The Earth is super bright. We get, a superb spectrum of almost infinite quality. The hard thing will be doing it, looking out there when the planet's 1 billion times fainter. It's, barely this tiny little blip next to a very bright star, and you're trying to get a spectrum to measure some tiny little, wiggle in the spectrum that indicates maybe the size of methane. But, of course, studies of our Earth's atmosphere are very important baseline to figure out what are the things we should be looking for in other planets' atmospheres. Great questions all.
Mike, can you tell us a bit about how you got into the field that you're in the first place?
Let's see here. Okay, so I guess when I was a kid, I was interested in space, and I read books on it, but I kind of forgot about it. And when I went to high school, I went to a high school that a lot of things were very good in the high school, but some of the science classes were not very good. So then when I went to college, I didn't know what I wanted to study, but I was sure I didn't want to study physics because I hated physics in high school. And then when I was filling out my schedule, freshman, I was trying to find things to fill out my schedule. I had an empty slot, and I was working with my student advisor, and we were flipping through the course catalog, and I was like, well, what can I use to fill this slot? And she's like, well, how about astronomy? I'm like, oh, astronomy. I used to be interested in astronomy. Why don't I sign up for intro astronomy? And so I took the class, and it was great. The professor was super interesting, very inspiring, and it just rekindled a joy in me. He offered me a summer research position, and that just sort of, set me off and going to remembering, how fascinating this topic was. And yeah, so I think, if I hadn't had an empty schedule in my slot, I probably would have found astronomy in the end, but that's the way it happened.
Bye.
Are there any other questions anyone would like to ask?
Yes, someone mentions I had to take some physics class. Yes, I had to take a lot of physics for astronomy, and I did. Some of them I enjoyed a lot. Some of them, frankly, I did not enjoy very much at all. And what am I working on now? Well, I'm working on trying to image more planets. I'm trying to find more of them, and I'm trying to figure out. I told you about spectra of planets. It turns out that interpreting the spectra turns out to be very difficult. So I'm trying to figure out better ways to interpret the spectra that we already have, to figure out more robustly how accurately we can figure out the compositions of these planets. Someone asked, what has been the hardest part of your career? That's a good question. I think there was a period of time, graduate school is a long haul. Graduate school is like 6 years, right? And there was a period of time in graduate school, like you enter graduate school, you kind of know what you want to pursue. It's very interesting. And there's kind of a middle phase of graduate school where you're like, is my project really going to work out or not? And then you're also kind of wondering, if I do this and I get a degree, am I really going to get a job? And so there was kind of a middle part of graduate school in my 20s where, I was kind of plugging away and, just kind of these big life looming questions were kind of hanging over me. That was, it was kind of a challenging time, but I think as we all know, at least most of us on the line, we get through our 20s somehow, and I did as well. Let's see, a question here about any book you would recommend. Oh boy. Not off the top of my head. There's a lot of good stuff out there now. Oh, someone recommends The Last Stargazers by IFA graduate. I believe that's Emily Levesque who wrote that book. That's a brand new book. That's actually a very good one. Let's see, an update on the health and schedule of Tmtr on Mauna Kea. Yeah, so the story currently, as you know, is that construction is suspended. TMT is awaiting, there's a study going on right now called the Decadal survey. Every 10 years, astronomers get together and decide what are our priorities for the next 10 years. It's a really big picture planning exercise. And one of the things that's being studied very intensely as part of this study is the 30-meter telescope. Should the US community, should the NSF invest a lot of money, close to $1 billion, and the project as a whole, close to $3 billion, to build these big telescopes? And the recommendation of this result, which should come out actually in 1 or 2 months, is the next big phase. If the proposal is top ranked, it'd say, yes, we must do this. It would be full steam ahead, at least from the funding side. Then, of course, we still need to figure out the very difficult situation here in the state of Hawaii in terms of being able to build on the sun Mauna Kea. People like Doug Simons have been working very hard with the astronomy community, with the telescope, with the local community, the Hawaiian community, to try to figure out a way to make this all work. Let's see here, what else is in the chat here? Stephen Hawking surprised me by saying that he thought humans would eventually travel to the stars. What do you think? Well, you know, what we understand now of, you know, physics, it seems incredibly difficult. On the other hand, you know, thousands of years ago, some people in Polynesia with wooden boats decided it would be a good idea to cast off into this huge giant ocean, travel thousands of miles and miraculously land on this little rock of Hawaii and do it repeatedly. If they could figure out how to do it, then surely, you know, sometime in the future, probably not in my lifetime, we can figure out how to do it as well. And I think probably we would want to. There's just some intense human imperative to explore. And it, you know, it's taken us all over the globe, and I'm sure someday it'll take us off our planet too. A question, has an exoplanet with an unmistakable biosignature been found yet? No, not yet. Biosignature is too hard with current technology. We are measuring molecules like water, but those we know can exist without life, gaseous water. So we are still more than a decade away from being able to measure biosignatures around another planet.
Okay, thank you so much, Mike. I really want to thank you for your presentation today. It was really interesting, fabulous. And also I'd like to thank all of you for attending our webinar today, and also the UH Foundation for their assistance in helping us to put together our webinar series. And we'll look forward to seeing you all soon. You'll soon be receiving an invitation to our next event, which is going to be held on October the 6th at 2 p.m. And this will feature Dr. Kimberly Binstead, who is in the Department of Information and Computer Sciences in the College of Natural Sciences. She's heading up the High Seas Project and will be speaking on preparing for space exploration while here on Earth. So please watch your inboxes for invitations to this event. We wish you all well. Hope you have a fabulous day or evening. And again, thank you again, Mike, for a fabulous presentation. Aloha, everyone.
Bye.
Thank you, Mike.